Hello again. This is where we left off last time with you reading this. Um, Very, very interesting. And the fact that water dissociates in itself, it auto-ionizes. Um, and what we do is we simplify this as these hydronium ions or H pluses. Um, but in reality, right, here's a hydronium ion here. We abbreviate that, simplify that as H plus. Mm-hmm. But, so H plus is one way to simplify it. H3O plus. This is actually a simplification as well. It's not a one-to-one ratio. Okay, and let me show you exactly what's happening here. The most accurate representation is probably something like this, where there's some number of water molecules that are surrounding those H pluses or those H3Os. Okay, water dissociating in itself, auto-ionizing. Remember when we learned about the dissociation of ions? Here's salt crystal being put into water, and the water molecules, because it's polar, partially positive, partially negative, actually separates the bonds between the chlorines, right? Surrounding it with this cell or this bubble of water where the hydrogens, the positive ends, are facing towards the negative ion, the chlorine in this case, making this whole thing overall bubble, this cell negative. Up here we have the sodium being surrounded by the negative parts of the water pointing to it, making this whole thing a positive ion floating in the water, right? So when you get too much concentration of this, that's when we don't have enough water molecules to surround all these ions, and so you get the solid particles at the bottom, right? I'll try that. But when you have water, here's what's happening. We have that hydronium that's forming, right? The water molecule, this water molecule up here rips off one of these hydrogens, and adds it to, darn it, adds it to, we'll just do it this way. Here's two water molecules, right? Rips off one of these hydrogens from here and adds it to here. So this would have three hydrogen atoms, right? Making this a H3O hydronium, right? This loses one of those positive hydrogens, make this seem OH minus, right? So you can picture that. If we come down here, where you can see, I've drawn this out, this hydronium now that picked up the hydrogen from this other water molecule, now has three of them, making this whole thing positive, gets surrounded by some number of water molecules. It really depends on the temperature. This N, a lot of them, they just bubble around it. They form this cell. Same thing with hydroxide. Gave its hydrogen to here, that reaction happening, and surrounded by all these water molecules. So this is how it actually exists. But it's a little more complicated than we have to write or think about. And so we abbreviate it, we simplify it as these H plus ions. Okay, here's the chemical reaction that's happening. You have your reactant of water, liquid. You could put aqueous, obviously. It's reversible, making these hydronium ions and these hydroxide ions. So this is happening throughout this liter of water, constantly, back and forth. It's actually dynamic. If we think about this chemical reaction happening, right, and we think about the concentration, the constant of dissociation for water, here we have our concentration of the reactants on the left, it's our water molecule, and our products, hydronium and hydroxide, simplified, of course. And so if we think about this, if we have a liter of water at 25 degrees Celsius, right, the concentration, the number of water molecules you can fit into a liter of water is 55.5 moles for every liter, right? So this is the molarity. Pure water actually has a concentration, molarity of 55.5 molar. Okay, and so if we think about how often does these water molecules dissociate in this 55 moles? Okay, and what it turns out is that as we have this many water molecules in 1 liter, okay, this is where this comes from, one water molecule will dissociate, okay, which means in a liter, this is the concentration. Essentially, this 55.5 would be the K, right, would be this concentration on the bottom, and this is the rate that it dissociates. Here's the equation here, and so this K, this concentration is the concentration of hydronium times the concentration of hydroxide. We call this the KW, the water dissociation constant, right? This ion product constant for water. Okay, so how much these water molecules dissociate. Okay, so this KW is always 1 times 10 to the negative 14th in a liter. Okay, so if we think about having this, looking at the concentration of the H plus or the OH minus, right? KW for this, these are going to be equal. I think I might have mentioned this, but for every 1 water molecule, if you look at the equation up here, for every 1 water molecule that dissociates, you get 1 each of these. So these are going to be in the same concentration, right? So if this is, you're multiplying these, this is equal to 1 times 10 to the negative 14th, what's the concentration of the hydrogens? What's the concentration of the hydroxide? Okay, think about this as your unknowns, and you know this is the rate that water dissociates. Talk a little bit more at 25 degrees. Then we have our unknowns here. We could say the concentration of H, we'll say that's X. It's going to be the same as the concentration of the OH, that's X, right? Is equal to 1 times 10 to the negative 14th. So that would be X squared is equal to 1 times 10 to the negative 14th. Concentration, molarity. Okay, so what's X? If you take the square root of both sides, the concentration of hydroxide and the concentration of hydronium would be, drum roll please, open this calculator up, square root of 1 times 10 to the 14th. Nope. 1 exponent 14 negative equals that. Oops. 1 exponent negative 14. Very, very small number. If we take the square root of that, let's see here. So take 1 exponent 14 negative. If I take the square root of that, I get 1 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. Negative 7. Okay, that's the concentration of hydroxide and hydronium. It's going to be equal, right? It's going to be neutral. Okay. Well, how do we usually, when we talk about acids and bases and neutral, we can talk about the pH. Okay, and so the pH, what that stands for is P is how much, how powerful, how strong is the hydroxide. Okay, there's also POH, which is how strong is the hydroxide, depending on what you're looking at. And when you multiply the pH times the POH, you're always going to get 14. If you take the concentration of this H plus times the concentration of hydroxide, you're always going to get 1 times 10 to the negative 14th. Okay? Where does pH come from? pH is the minus log of this, right? So the pH of water is usually 7 meaning neutral. Well, what does this mean? If I take the minus log of 1 times 10 to the negative 7th, it's still in here. If I take the log of this, that gives me negative 7, and then reverse the sign of it, 7. So the pH of water is 7, and this is why. Because water ionizes in itself. It dissociates in itself at a very constant rate, giving us an equal amount of hydroxide to hydronium. Go into this a little bit more detail in this next slide here. pH, right? Instead of writing the concentration of hydroxide, you get these really, really small numbers. Usually you don't want to write 1 times 10 to the negative whatever, right? So we simplify it, kind of, by using this pH scale, okay? And the pH scale is a lot easier. It's convenient. But what it is the negative log of the concentration of the hydrogen ion, if you're looking at how acidic something is, okay? So if you know the concentration of the hydrogen, the H plus, here, take the minus log of that, and that gives you the pH. Okay, it's a negative logarithmic scale. That's why a more acidic is lower, because it's negative, right? And it just doesn't get bigger, more acidic by individual units, right? pH of 0 is exponentially bigger than a pH of 7, right? It's a logarithmic scale, okay? If you know the pH and you want to figure out the concentration, because this is easier to use mathematically sometimes, if you know the pH of something, what you're going to do, because it's base 10, this logarithmic scale is base 10, you're going to take 10 to the power of pH. So the pH of water is 7, and so you take the power, and that would be the negative. And so the pH of water would be 1 times 10 to the negative 7th, right? That's where that comes from. That's where pH is based off. If I have a little better understanding of pH, because we used it for probably since middle school, but now this is actually where this comes from, okay? It's a term from a Danish chemist name. There's his name. I wish my first name was the same as my last name there sometimes. Soren Peter Sorensen. Might be Casey Peter Grangensen, right? Kind of cool. But here's the German word for hydrogen ion exponent, this pH. Wasser. I've been learning that German is really actually close to English. Wasser means water. Stoff means water stuff, right? Ion, okay. Exponent. I don't think this should be. There's a mistake there. I think I should have this N, this EN in here. I'm not sure. Look that up. Waterstoff ion exponents, right? It's actually, right, it means German hydrogen ion exponent, okay? And so that P, we use that P for this German word potens, which means power, okay? So that means just how much hydrogen, or specifically hydronium, is there, okay? So it's base 10, gives you the strength of the acid. So pH, and pH, you have to remember, does not have units. One of the only times in this class, right, you don't have units. But that's what it is. It is the scale, logarithmic scale, base 10 of the hydrates. So that's why you can read this. This is why the pH is more acidic, is lower, right? It's inverted. It's negative. Technically, it can go from negative to above 14. Usually you talk about 1 to 14. You can actually go 0 to 14. You can actually get acids that have a pH of negative. I think the most strong one I've heard of is like negative 3 or 4 or something, all the way to, you can have something as basic as 15, 17. It's kind of interesting.